Let's say we have an abstract triangle. One angle is 90 degrees, and the diagonal side has a length of 1. That leaves 2 sides and 2 angles adjustable. Our triangle could be any one of these options. Believe it or not, this niche shape is the foundation of the most useful type of geometry, trigonometry, or just trig for short. And if you know anything about trig, you know it's all about them triangles. The word literally means 3-angle measure, but our triangle is a very specific type. It's a right triangle, so named because 90-degree angles are called right angles. So they're the only correct angle? Give me a break. No, this use of the word right is left over from a Latin term meaning straight, because that angle makes a side that's straight up and down. That's just what it's called now. Roll with it. Of course, triangles exist that aren't right, but all of them can easily be divided into right triangles, so right triangles are a great building block. Why did we decide the diagonal should have a length of 1? Because this is a unit triangle, and units are the perfect building block. Here's the thing though. For trig to do what we want it to do, it needs to relate the sides of a triangle to its angles. Let's just consider one of those angles for a moment. If we change that angle but keep the diagonal the same, the other 2 sides change accordingly. The length of each depends on the angle. In math speak, we'd say the length is a function of the angle. Eventually, we'll need to know what those functions look like, but more on that later. For now, we're just naming them and getting a feel for relationships. The length opposite the angle, let's call that sine. S-I-N-E, sine. Why is it called that? Well, there's some debate about this. It might have been a mistranslation from Arabic to Latin, but it was probably a boob joke. Humans have always been crude. There's no way to know for sure though, so believe whatever you want. Okay, back to our triangle. This length is called the sine, but we also need a name for the other length. It happens to be opposite the other angle, which makes it the sine of that other angle. That angle is called the complementary angle. So this length is the sine of the complementary angle, or cosine for short. Man, I love it when a name makes sense. Okay, cool. We have special functions for the sides of our unit triangle. Now let's build bigger triangles with it. Most don't have a diagonal of 1, but if the angles match, the triangles are similar. Yes, that's an official math term. Similar triangles are proportional in size. Is the length of your diagonal 2? Well, then the other lengths are 2 sine and 2 cosine. Is the diagonal 100? Well, then the other lengths are 100 sine and 100 cosine. We can write this pattern more generally. It now applies to any size right triangle. And remember, you can split any triangle into 2 right triangles. So if you're careful with your labels, this rule actually works for all triangles. Your scientific or graphing calculator knows what sine and cosine look like. So if you've got that, you can do some good practical work. But let's be honest, if you've come to my channel, you're here to understand, not to do. So let's go a little deeper. We've got a good handle on a few special angles: 0, 30, 45, 60, and 90 degrees. Let's start with 45 degrees. In this case, the angles are equal, which means the sides are also equal. Pythagorean theorem gives us the number. Like I said, we've got a good handle on these. They're the low-hanging fruit. At 30 degrees, the opposite side is half the diagonal. We know this because 2 of them form an equilateral triangle. Never forget, these right triangles are building blocks. Anyway, Pythagorean theorem gives us the other number. At 0 degrees, we take this to the extreme. The opposite side is clearly 0, which makes the diagonal and the bottom sides the same. The 60 and 90 degree cases we get from symmetry. They're the opposite of 30 and 0 degrees, respectively. These angles we know very well, but the rest aren't so obvious. What are the values for sine and cosine at, I don't know, 33 degrees or 72 degrees? To figure that out, we need to go all the way around. This doesn't just stop at 90 degrees. It goes to 360 degrees and keeps going. The outer corner of this unit triangle draws an entire circle, which we call the unit circle. This circle is simply the set of all unit triangles. That's it. Traditionally, it only shows numbers for a few special cases, but it encompasses every angle. And we can use it to figure out what sine and cosine actually look like. Sine might be this side of the triangle, but it's also this length over here. They're the same, because rectangles. Now, let the angle go around at a steady rate. If that sine length were to draw on a scrolling piece of paper, out pops a wave. This is what the sine function looks like. We can do the same thing for cosine. We just need the paper to scroll up and down. But if we superimpose them, we can compare. It turns out sine and cosine are the same function, just 90 degrees apart. Which makes sense because that's how we defined cosine. It's the sine of the complementary angle. It is a sine function. That just leaves the other trig functions: tangent, secant, cotangent, and cosecant. All four of them are on the unit circle too. They're just not necessarily inside the circle. A tangent line touches a shape at one point. Tangent literally means touching. The tangent function is a segment of the tangent line. It goes from the outer corner of the triangle to the horizontal axis, because that's the part of the line within the angle. Just like sine and cosine, this changes as the angle changes, which makes sense. It happens to be equal to sine divided by cosine. For secant, we're gonna have to think a little more outside the box, circle. This tangent forms a larger right triangle with the horizontal axis. The length along that horizontal axis is the secant. Secant literally means to cut. This is the line that cuts off the tangent to give it the length it has. It's literally cutting through the tangent line. And you can see it also depends on the angle. We get cotangent and cosecant the same way we got cosine. They're the complementary versions, so they're simply found on the other side of the diagonal. Now that we have every modern-day trig function on the diagram, we can see how they all relate to each other, and how they all change as the angle changes. So what do all these functions look like on a graph? They're not as pretty as sine and cosine, but we can still figure them out. The unit circle shows us that tangent goes to infinity in a couple of places, and has a value of 0 at 0 degrees. That looks something like this, and that pattern repeats forever in both directions. Cotangent is the complementary tangent, so it's just mirrored and a little shifted, but basically the same. We can do a similar thing with secant. It looks like this. The cosecant is the complementary secant, so again, it's just mirrored and a little shifted. What I like most about these two is how they compare with sine and cosine. Kind of beautiful, isn't it? Okay, but how is this the most useful type of geometry? Triangles are the strongest shape, which is why we use them in bridges and other support structures. Speaking of which, please consider supporting my work. It'll get you access to exclusive content, links in the doobly-doo. These triangles don't have to be tangible though. Say you want to measure the height of a building. Could you make a really long tape measure? Sure. But why not just measure the easier length along the ground and imagine a triangle? The same goes for measuring the distance across a river. And if you're doing physics, you're probably working with vectors. Got a vector that doesn't line up with your coordinates? You're gonna need a triangle. Triangles are everywhere. They're the best shape. And until next time, remember, it's okay to be a little crazy.
I think you're just getting in your head about it.
I wanna make sure I'm enunciating the word diagonal.
Yes, if anything, you are over it.
Diagonally.
I feel like we're gonna end up with pen wings here in a second.
Right, pen wings. Mirrored.
Mirrored.
Mirrored. Secant, more like secan.
Nerd.